Excellent. Hey, everybody. All right. Nice to meet you all. How many people do we have now? 77. Cool. All right. Yeah, well, thanks for having me here. Thanks, Seth, for recruiting me and being patient. I know it was a little bit of cat and mouse, but I did take your recommendation for hairstylist. So Giovanni sends his regards. I'm going to speak today about some work that we're doing in my lab that we're excited about. That is, I want to be fully upfront. It's sort of like a blue oceans area for us, in that it's applying ideas and the kind of conceptual frameworks of causality, but in a regime which is natural language processing, where we don't have the kinds of sort of simple reductive, like well-defined causal structures that like the sort of mathematical machinery of causal inference relies upon. And so, the high level here is, finding clever ways to use humans in the loop to sort of perform some of the kinds of interventions that execute some of the primitives that we associate with causality, and to get at concepts that feel and are in some sense, causal or counterfactual in nature. And at the same time be working with data where, that kind of structure is sort of seldom, explicit. So I'll introduce myself a little bit, since Seth encouraged that. So my name is Zach. I am currently a professor at Carnegie Mellon University, and my appointments are split among the machine learning department and the operations research group. So operations research sits in the business schools at other places. It sits in the engineering school at other universities, but basically they're the people concerned with making decisions, often addressing things like hard combinatorial optimization problems and optimization, maybe more broadly. Whereas in machine learning, we maybe traditionally think more than anything about prediction, or if we think about decisions, it's usually in the context of a kind of idealized setting, like a typical reinforcement learning setting, where you don't, think about things like confounding. And I think these worlds are kind of starting to collide in interesting ways, because I think the first step was like machine learning didn't even do prediction well. And so the first step was, getting to machine learning models that can make accurate predictions on the kinds of messy real world data that we actually have lots of. And we've sort of crossed that. There's a lot to be done, a lot to be formalized, but we sort of crossed that threshold. But now we're getting to this weird space where people are sort of thinking, well, now that we have these models and they sort of work for the thing they were ostensibly trained for, what do we do with them? And that's where kind of shit hits the fan, because machine learning was sort of never about decision making in the first place, and it's unclear, under what conditions the outputs of models actually provide guidance for how you should make, what categories of real world decisions. So with that maybe preamble, I could say a little bit about my lab. So at CMU, I run a lab that we call the Approximately Correct Machine Intelligence Lab. And this is a little bit of a double or triple entendre, in that it's on one hand, we do some amount of theory of machine learning in the lab, and there's a probably approximately correct framework for characterizing learning algorithms, which is sort of like all that we can do when we're estimating things from data, is say that we're so sure that something is so close to true. But we're never able to make sort of exact statements. But I also have found the term, and it's the name of a blog that I've run since I was a PhD student, was Approximately Correct. I found the term, cute in the sense that there's another sense in what we're doing. What we're always doing is approximately correct, which is that we're almost always solving a problem that is not exactly the problem we really care about, not exactly the prediction target that ideally we'd be trying to predict. Not exactly related, one-to-one to the decision problem we actually think we're addressing. And so there's a way in which the technical solutions that we come up with are always at best approximate in a more profound, maybe like conceptual way, solutions to the real world problems that they're ostensibly addressing. So we cover a lot of ground in the lab, and today I'll be speaking a bit about ideas in causality and about natural language processing and some connections to concerns about robustness and social impacts. Of course, the models we'll be using are deep learning. So I guess the only box we're not ticking here is healthcare. But maybe you'll get a flavor of how these things that seem like disparate research interests actually are kind of related, which is broadly, we're concerned with the outer loop. So the inner loop is like, I've got a training set, I've got a prediction target, let me iterate on model selection, hyperparameter tuning, parameter learning. That's the inner loop, all of that. For me, the outer loop is questions about what real world problem do we think we're actually addressing? What aspects of things that could happen in the real world, like for example, distribution shift, are we accounting for or not at all? And that includes also, other sorts of real world desiderata associated with decisions that are not necessarily expressed formally in machine learning setups. And this includes, concerns about justice, whether it's like a kind of group level, like a comparative justice concern, or questions about procedural justice. But if you use machine learning to, for example, decide who to grant a job interview to, or who to send to jail, or no one explicitly decides who goes to jail just based on the output of a model, but people do look at say risk prediction scores and give these to judges to potentially influence their decisions. So sort of broadly looking at these concerns that sit outside the inner loop, and that generally I think machine learning practitioners have a tendency to approach extremely naively, to sort of just pretend that they're technical problems, to say, oh, what if we add an adversary, or what if we add more layers? And sort of one of my takeaways here is going to be that these are actually more profound problems, and that kind of like naive mindset for coming up with solutions isn't even addressing the problems, let alone solving many of them. All right. So some broad context, deep learning is here. Every 12-year-old knows how to implement, some kind of battery of fully connected and convolutional and recurrent and transformer-based architectures in PyTorch or Keras. We get good performance as assessed based on sort of IID accuracy as assessed on a high IID holdout set. For tasks where the real label is something that people can actually recognize somewhat reliably. And on natural data sets, even, and I don't mean to downplay it, these are things we couldn't do 15 years ago, even data sets that are extremely high dimensional, where there's no good theoretical reason why we should assume that we could in general, come up with a classifier given the amounts of data that we have. And this, includes, say, classifying or recognizing objects in high dimensional images, or working with long documents the way we can now. And at the same time, there's some trouble in paradise, right? It's not that just everything's going great, it's that we have this powerful hammer for the thing, explicitly the thing we trained it for. And if it turns out the thing we trained it for, which was to make accurate predictions, these models are making accurate predictions. And when I say that, I mean, they actually generalize to previously unseen data. However, it turns out maybe that's not exactly a perfect description of what we cared about in the first place, was just, in expectation, having a low error rate on unseen data from the same exact distribution. And so you're starting to see all these papers that are writing about, oh, the model didn't really learn the task, or it learned the wrong features, or it actually doesn't, it didn't really learn the task because it just picked up the artifacts, or, it is biased. But, when people say biased, they often don't necessarily mean in a coherent statistical sense. What they mean by biased is it It, it treats, instances that are different on some feature differently from each other, even though we don't think the model should. But the question is, what is this thing that what the model should be responding to? All we ever formalized was a paradigm for learning from examples, and it's not clear what is a superficial association or a spurious association. So you have lots of papers that are just sort of groping in the dark and sort of just using these words, the bad patterns, the bad correlations, it's a normative assertion about there are things you should and shouldn't be sensitive to. Of course, what it means to be sensitive, not articulated clearly in the papers. What any of these terms really means, not articulated clearly in the papers. And whether even what they mean, if they were able to articulate it, is something that you could actually expect any model at all to do, is not explored because they haven't gotten that far. You have to concretize something to be able to address it. And so my point in this talk is not going to be to say that these concerns are invalid. Quite the opposite. It's going to say these concerns are getting at vital problems. They are naive expressions of well-founded concern about something that's missing from our whole way of doing learning. But at the same time, I'm going to sort of argue that we have to, in order to address these problems, we have to think a lot more seriously. So something that I'll come back to hopefully is maybe I should take a poll or something. I don't know if that's possible, but if people are working, how many people have encountered problems of identifiability in their research? And my guess is that if this is a mostly NLP or ML problem, most people have never thought about identification problems in the first place. I mean, like to identify a parameter or to develop a consistent estimator. So I don't know if I should look at the chat or the.
Yeah, unfortunately, I don't think I can set up a poll on the fly.
Yeah, well, Jinya has, but maybe Jinya's in the minority. So, right, as Mohammed is talking about the natural sciences, this is great. I mean, it's the natural sciences where you think about these things very clearly, because a theory suggests there is some underlying parameter, and the question is, what do we measure, and how can we, based on the measurements, back out to some underlying parameter in nature that we care about. This isn't a status quo. This isn't the standard practice for most machine learning, certainly like most industrial deep learning. There, we're usually just saying, hey, I want to find the best predictive model in the class. And that's a problem where it's sort of, if the features are given, and the labels are given, it's sort of, you don't have a question of identifiability, meaning like you have a question of coming up with the best model, or the best model you can come up with, like searching for the best model. You have the optimization problem, but you don't have a question of identification in the first place, and that's different from, say, in causality, where you want to say identify a treatment effect, and there's a question mark even before you begin, which is it even possible, given the measurements that you have, to estimate the parameter of interest? And I think that a lot of these problems about spurious associations really require that we think in from this like identification mindset, right? Like if there's bad correlations and good correlations, so to speak, is there any way to just look at a data set and say, oh, these are the bad ones and these are the good ones? Or is this something that actually, is not necessarily, preordained? And so I'll kind of explain, and we could go back and forth in QA, but, maybe like a clear argument for why, in general, we should not think that, the superficial or the spurious is something that is actually identifiable from the data alone, but that it actually requires some exogenous specification. And the question, perhaps the question here that we address is how do you elicit that? How do you elicit that exogenous, that additional information? So let me give you like an example of a problem, how this can manifest and why you might find it troublesome. So, and this is, still very hand wavy and gestural, just the level of building intuition. This is the kind of thing that people, get worried by, is you say, well, let's just train a movie review classifier to distinguish between positive reviews and negative reviews. And you start finding that, so romantic comes up at the top, but also, and this isn't here, romance also shows up as one of the top 20 positive words. So I literally hear you train a linear SVM on TF IDF features, and you just look at like the coefficient values, the most positive and most negative words. So again, that's a very kind of heuristic way of building a model. Even here, what we mean by interpretation is a little bit dubious, but I just want to kind of convey a little bit of intuition here that, if we looked at the full set, the word horror and romance, are both super polarized, even though neither of them by itself, actually semantically communicates sentiment. Like a movie can be again, romantic, you could quibble, but the word romance is also up there. It's like in the top 20. Romance is a genre. Horror is a genre. You can have an amazing horror movie. I think we're experiencing a little bit of a renaissance in horror movies in this present moment. But historically, I guess many of them are low budget, or for whatever reason, there's some kind of confounder. The words are predictive. The genre words are predictive of the review sentiment. But in some sense, you feel like it seems wrong that the model should rely on this, because this isn't what makes the sentiment apply. So the question is, how do we formal this idea? And let me give a few more examples of motivation, just so you see this sort of this general kind of problem of people kind of groping at this sort of thing. Like the ImageNet CNNs are biased towards textures. So what they do is they say, okay, let's look at this patch of elephant skin, classified very confidently as Indian elephant. This shape cutout of a tabby cat, classified confidently as a tabby cat. But if you impose that texture on that shape, then it's predicted, fairly confidently as an Indian elephant. So they're sort of saying the model is biased towards texture. But again, what does it mean to be biased? Is there any way that the model, what is the coherent framework within which the model, like you will never have seen, maybe it's a cat tattoo on an elephant skin. So maybe it should be Indian elephant, Like what is the principle according to which the model should have decided that one of these, relying on those features is bias, but the other one is, signal or something. Like what does bias really mean here? And it's not any sort of clear technical definition of bias that is, familiar, like the systemic bias of a particular, statistical estimator. So you see all these different things, like where models, classify, whether it's an insect or a bird, based as much, on things like the background or the coloring of the image. So here it's an insect confidently, even when there's no bird or insect. Or if you change the color of it, it becomes a bird. It's like what, there's some sense in which you think the thing on the right should be classified as an insect and not a bird. Again, what is the principle that says the shape is more important here? There's the classic cows on the beach example, or elephants on the beach, or whatever, where it's like, if the cow is in the pasture, very confidently cow on the beach, confidently not a cow. We've encountered similar kind of issues where you have this task of natural language inference, right, which is a dubious name for the task in the first place, but NLP is the home turf for dubious names for tasks. Perhaps less dubious than reading comprehension. But there's this, basically at a high level, if you have two sentences that are in some kind of posture with relationship to each other, either one entails the other, one contradicts the other, or they're in some kind of neutral relationship. And the idea is you should classify, it's basically just a three-way classification task. But it turns out that the way the data set was created was something like there was a set of premises that were given, and then workers were asked to come up with hypotheses that made different labels apply. And it turns out as a result, there's, you can't predict the label given the premise, because the premise, any premise is equally likely to be assigned to any label. But if you predict based on the hypotheses only, it turns out you can get similar performance to the best NLI models. And it raises the question of, well, why should I think that the model was doing anything to assess the relationship between these sentences in the first place, if I didn't even need the premise to get that performance using more or less the same model class. You know, and we've, you know, seen all kinds of examples. There's the well-known cases of adversarial examples. So that's, you know, sort of small, localized, you know, low L infinity norm perturbations in images can bring down the performance of image classifiers dramatically. In a paper in ACL with my student, Danish Pruthi, and our good friend Bolan Dingra, incoming professor at Duke. So I recommend, you know, anybody in North Carolina or just anybody who likes good weather should go to Duke and do a PhD with Bolan because he's the best. But anyway, my advertisement over. We found that basically, you know, there's no imperceptible edits in text like there are in images. But, you know, unless you have like lowercase L's and uppercase I's that are, you know, depending upon like the sans serif font face might be identical in rendering. However, there are some well-known cognitive studies that people can basically make sense out of whole paragraphs of text if you scramble the internal letters, as long as you keep the first and last letter of every word the same. And so we show, for example, with like character swaps, a single character tap can bring down a BERT level, a state-of-the-art BERT model to below the performance of random guessing. Obviously, if you can manipulate, you know, greedily, now attack a second character, you could bring it down, you know, way below random guessing. We had a very similar result to the hypothesis-only baseline result in EMNLP 2018. So my student Divyansh had a nice start to his graduate career and like got the spring of his first year of master's, got this best paper award for the best short paper at EMNLP for a paper that honestly we shouldn't have been able to write, but we were only able to write because of kind of the confused state of the field and the sort of rush to create benchmarks in a way where maybe we don't really know what we're benchmarking. A similar kind of thing that for many of these reading comprehension data sets are, you know, better described as passage-based question answering data sets, you can get whatever is the state-of-the-art performance, you could get that either by looking only at the question or only at the passage. So you might say, how could you look only at the question? Or what does it mean to destroy all information in the passage? One way you could destroy all the information in the passage, if it's a span-based extraction, which means that the answer still has to be contained there, is you could just keep all the candidate entities in the passage, replace all the rest of the text with, you know, first place them in random order, and then infill all around them with just random words. And if you train on that data, you also get, you know, more or less the same performance as the state-of-the-art models, and that suggests like, hey, how do we know we're actually doing question answering at all? Because, you know, the model's clearly able to get the same reported performance without there being any, you know, any even possibility of comprehension. So why should we care? Why is it a problem? If the models are accurate IID, why should we care? So I don't know, maybe I'll open it up here and stop for a minute. Why does anybody feel like we should care? Does anyone feel strongly that we shouldn't care? You know, like I'm sure I could dig up a quote of like Jan LeCun somewhere and be like, if the model is accurate, what do we care about? So, you know, why should we care? Because the thing is not doing what it says it's doing, and that's a cute answer, Gabriel. But I'd push, you know, to make you know, a stronger argument in that, I don't know, if I told you that my robot was gonna perform life-saving surgery, you know, because it was, you know, I don't know, because it was a medical genius, and then it turned out actually it was just following some simple program, but it still, you know, in general performed life-saving surgery more reliably than a surgeon, and it saved your life. Would you really be that upset? So I guess I'd push you to like formalize a, you know, maybe a more not just an argument about, you know, does it do what people want to say it's doing, but rather like, you know, is there actually something, is there actually like a real or a desiderata that's like unmet that, you know, is something that, you know, things that we actually should care about? Without understanding, there is no science. Surely. And let's be clear, what's going on in these papers is certainly not science, not natural science. However, even if, so I think it's a good answer, and that like if our goal in modeling data is to extract scientific knowledge, then I think that right there's, we can trip out and talk about Thomas Kuhn or something, but it's like there's does data tell us anything absent a paradigm? Is there any understanding without theory? And the answer is quite possibly no. Certainly smarter men than any of us, and women too. Forgive the anachronism. Have certainly made that argument. But there are other reasons. Some models are wrong, but that's I don't know if there's an argument for or against. Surely these models are useful in some sense, but the question is, why? Okay, no real world data is IAD, I guess. Okay, it's a good answer. My slide sort of is hinting at that direction, right? So one reason why is because the model's not actually just like our test is actually a weak sort of test. That the model will perform well only when seeing data that is sampled independently from the exact same underlying distribution. That's not something in general that we can count upon. There's other reasons, right? Like, we're not often just making decisions, and we're not often just dealing with, making predictions or just dealing with statistical data. We are actually in a world populated by multiple agents, and we have obligations to them, and we have responsibilities. And some of these include, commitments to things like procedural fairness. Like if I tell you that if you wear a pink shirt, I won't hire you for a job, this is, maybe if there was data that said that pink shirts were predictive of, whether or not someone got promoted or in a year later for who knows what reason, who knows what confounding, but is that a valid basis for making an employment decision? And an argument that it's not should be maybe a causal one. Says, hey, people can should be allowed to make whatever choice they want to make about what kind of shirt they wear, provided that they wear some kind of shirt. And we understand enough about the mechanism by which the world works that any one person intervening on what shirt they wear doesn't make them a better or worse employee. And so we shouldn't require people to we shouldn't be creating incentives where in order to get some kind of opportunity, you have to take this action that actually is irrelevant. So this starts to make more sense if you think in the sense of a kind of causal structure, right? When I say causal, I mean thinking about primitives like interventions. The idea of someone who otherwise would have worn the pink shirt deciding not to wear it. So it's like you might say, oh, but it's predictive, but it's not predictive in the world where people respond to the incentive, right? If everyone says, okay, well, if you don't hire people with pink shirts, I guess we wear no more pink shirts, then this is no longer a very accurate model. It was relying on this feature that no longer has the same relationship to the target. So, this relates to this whole literature on strategic behavior, but it also just broadly, just calls out this fact that like what we are doing in general is not prediction. We are creating working systems that we're trying to set out to drive some kind of automated product, and people are engaging with them in all kinds of strategic ways. And we want a model that is going to continue to work in the real world. Even now in general, like spoiler alert, you might say we want a model robust to distribution shift. And you'll see tons of naive papers in the deep learning literature that say, oh, we added again and did this adversarial thing. And now we have this representation that's robust to distribution shift. Anytime you see a claim like that, if it's unqualified, it's absolute nonsense. It's basically, in general, distribution shift is an impossible problem because you fix any classifier, there's some distribution of data where that classifier is the worst possible classifier. And so the only question then is, under what conditions is it possible to be, for a model to generalize across, families of distributions, situations that you might encounter. Question in the QA. Seth Levine, we have to understand the decisions that machines and AI are making because over time they'll continue to make more predictions and influence their behavior. Yeah, that's, I think, exactly, in the spirit of what I'm arguing. Kat asked a question about the QA stream being listed in the chat panel. I think this is a question for Seth. Yeah, anyway, so cool. So I'm going to introduce one idea that we had. And the idea is basically getting at this question of, you know, what does it mean for data to be, or for features to be spurious? And what does it mean even in a world where what constitutes a feature isn't even so clear? Like raw text, you know, is a feature like patterns of words, is a feature individual unigrams. So the high level idea is, you know, spuriousness is not a well-defined term in this sort of like deep learning is learning the bad correlations literature. But, you know, spuriousness actually has a, what it means to be spurious is well-defined in other contexts. So there's a statistical definition, which is not what any of us mean here, which is you might say that a spurious finding is like one that like basically will vanish if you just collect more data. It's something that there appears to be a correlation, but only it's sort of a false discovery because of small sample size. And that's not what any of us actually are talking about here. There's another notion of spuriousness that is, I believe, very closely related to what people are trying to hint at here, which is in causality. And in the causality literature, a spurious association is one that arises due to confounding. Confounding is sort of an overloaded term because, you know, people might be like confusing or something. But confounding in the context of causality means something very specific, which is having a common cause. So for example, if having a low budget makes me more likely to make a horror movie and also more likely to make a bad movie, this means that, you know, it's neither the case that being a horror movie causes the movie to be bad, nor that being bad causes it to be a horror movie, but rather that both are sort of results of someone being given only a low budget to make their films. You know, I don't know if that's actually true of horror movie creation. It's not my industry yet, but that's, you know, cool. Thanks, Mike. Right, so spuriousness refers to these associations that arise only due to common causes, but not actually due to either a direct influence of one variable on the other. So the idea is now, like, how do we get at, how can we formalize this in the context of NLP? And I'll kind of get to some models, some more formal models in a minute if we're able to get there. I guess this talk has like a natural end, and then it has like a natural extension, although I think we might be able to get there. But, you know, we could think of it as something either, like we could actually either think of the label, something like the sentiment of the review, as like one among some number of latent factors that directly cause the sort of text in the review alongside the other latent factors. And we'd say, we think of like a spurious association would be one that doesn't change if we were to just intervene on the sentiment, or we could flip it around. We could say that, you know, the words themselves cause the perceived sentiment of the annotator. And a spurious, you know, relationship would be, you know, it would be if a word was predictive, or, you know, if some chunk of text was predictive of the label, but intervening on it and changing it to something else wouldn't actually flip the applicability of the label. So we get to this idea in both cases that there's this question about the relationship between, you know, we got to think of like flipping the label and getting the text to change, or having the person change the text to flip the perceived label. And so this is, I'll get really concrete now, and then I'll zoom back out to like, you know, the kind of conceptual framing of what we do. But the high level is we propose something that we call counterfactually augmented data. And you're probably used to seeing like crowd worker schemes where you just say, here's a document, give me the label. Here's a document, give me the label. And what we do instead here is something different. We already have a data set for which ground truth labels are already known. So in this case, they say movie reviews, and we already know, are they positive or negative sentiment. So we have the original data set, and what we do for each round, every time we encounter a crowd worker, in this case, they're not really annotators, but they're really editors. We sample a point from the data, we present it to the annotator, and we basically say, here is the original review, here is the original label, here is that same review in an editable text box, and now your job is to revise the review to sort of accord with a counterfactual label, some label other than the original label. And I'll get into the exact instructions soon, but the idea is that, so we start off with this original data point that had one label, and now we have this new data point, which is sort of like its, you know, mirror image from an alternate universe. This was the positive review. Now we have the negative version of that same review. And now we have a new data set where basically, you know, subject to, you know, now we have another round of crowdsourcing where people have to either approve or reject the new counterfactual data point in terms of both how it agrees with the original data point on all non-crucial matters and whether it agrees with the new counterfactual label. And if it's approved, we add it to the data. So now we have a new data set. And we basically have the original data, the revised data, and then we could pool them together. And this gives us what we call the augmented data set. Let's walk through the platform again a little bit. You can see the top part is just an example, and then the bottom part is the live interface. So in the top, you see basically you have a review, the original label, in this case, a positive. Then you have below it the same review, but the person's supposed to edit it. And the goal is to edit it so that it accords with a corresponding specified counterfactual label. So it was originally positive, and they say, here, edit that review to make it negative. And the points are they have to edit it to make the counterfactual label apply. They're supposed to edit it thoroughly enough that the review is internally consistent. Like they shouldn't leave the review in a kind of like, you know, some of the sentences are positive, some of them are negative. However, and this is a crucial point, the annotators are basically instructed, do not edit the review in a gratuitous way. Basically, do not edit any portions of the passage like unnecessarily that don't need to change. And so, you know, we give them some discretion to interpret this, but you know, what we basically mean is, you know, if something doesn't need to change to flip the, you know, it's not relevant to flipping the applicability of the label, don't change it. Don't change points of fact. Don't change, you know, points of style. And so if we look at what's happening here, I just want you to like think about this a little bit, is that we started off, say, with a bunch of reviews, and they were all reviews of horror films. And they were all negative because all the horror film, you know, the vast majority of horror films are given negative reviews. A tough crowd. But then what do? People take all those reviews, and all of them have been edited so that they're now in the new revised data, they're all positive, right? Because every negative review became a positive in a bizarro universe. Every positive review becomes negative. So all these negative horror reviews are now positive reviews, but they're not just positive reviews, they're positive horror reviews. And the reason why is because the human knows what is the difference that makes a difference. And the human knows that, you know, genre is not what makes sentiment apply. And that if you just fixed every other aspect of the film and flip the sentiment, you don't change whether the person calls it a horror film. And likewise, you know, you could say, if you just change whether, you know, changing whether you call it a horror film or a romance film doesn't, you know, make the review more positive or negative. Cool, just checking the chat. So right, this is the idea. And you know, sometimes people say things like, oh, crowd workers aren't that creative. My experience is, I mean, maybe part of it is that we paid them well and that like we took this seriously. And we took the time to make clear instructions. We were kind of painstaking about every aspect of this. And the code and interface are also freely available if someone wants to build on this. I think another part of it is that workers are sometimes, if you just ask them to like generate a paragraph on the spot, that's a difficult thing for people to do, but you give them some context and you tell them they're trying to edit something and to make it mean something else or whatever. It's like a little bit more context, people know what you mean. And we actually found that they were really interesting and creative, and these weren't just like people going in and sticking the word "not," you know, in a bunch of places. They weren't like, this review is, you know, this movie is not good. You know, they weren't like Borat style reviews. They were, I think, you know, significantly more thoughtful. And they, they had all kinds of interesting ways. Like they would sort of hedge. They would take, things that were compliments and hedge them. Like hidden beneath the world of Atlantis, blah, 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 is supposed to be fantastic, or they might take something that was like positive, but they might sort of put it in quotes to sort of, indicate like sort of sarcasm or skepticism. They might just flip, modifiers, take something that was cool, make it lame. So they kind of stayed within style, but they found counterparts. They might sort of insert, insert some kind of phrases into sentences, or, delete some phrases, or they might hedge some comments by making them, like temper some things. So it becomes more and more intriguing. It becomes only slightly more intriguing. So people came up with all kinds of ways of editing these reviews in clever ways that, changed the sentiment of the review, but really didn't change any of the substantive facts conveyed in the review. Nor did they even change, that much the style of the review, which is interesting. So again, going back here, these were the original salient features. And I'm going to show results of experiments with SVM, naive Bayes, BiLSTM models, pre-trained BERT transformer models. A lot of the qualitative insights carry over when we look at performance trained on one data set versus the other versus both, et cetera. But I just want to use the SVM just to, kind of tie the talk together and go back to that original example where when we say, what are the most important words, I want you to notice that, okay, horrors, we have bad, worst, boring, awful, terrible, poor. Those all make sense as bad words. Bad words meaning like conveying negative sentiment. We also have, it's not just horror, right? You have horror, something, nothing, seems, effort, dawn. I don't know why dawn. Maybe it's like mafia movies aren't, popular or something anymore. Who knows? Then the positive reviews, have both life, especially. You could be especially bad. You don't have to be especially good. Unclear why, some of these things showed up as most important features, but for whatever reason, they are predictive. Has, my, well, will. So there's a bunch of these words here that just seem like they don't belong. But there's also a bunch of words that, seem like they do. Great, fun, excellent, wonderful, perfect, love. So again, I don't want to put too much credit onto this kind of interpretation, but I want to convey something of a qualitative insight about what's going on here. So that's, when you train on the original data and just look at the model. Now, anybody want to guess what happens if you train on the counterfactually revised data? So this is not the original data, but the counterparts, where each, it's the edited version of each review and the counterfactual label, but not the original reviews. Anybody want to guess what's going to happen here? Right, the genre switches places, exactly. But the interesting thing is the genre switches places, but not all words switch place, right? Boring, worst, terrible, bad, awful were among the most negative words, and they still are. Interesting, amazing, best, funny, fantastic. They've changed the order a little bit, but they're still all super positive. But horror, which was super negative, has flipped to positive. And romantic, which was super positive, is flipped to negative. Now, interesting thing happens further is that we can train on both the original data and the revised data and see what happens. And when we go there, basically all of those words fall out in a kind of strange way when you train on the original and the new. So you have worst, boring, bad, terrible, awful, not, poorly, dull, poor, fails, horrible, worst, predictable, badly, hated, hate, stupid. For some reason, dawn is still in there. But basically all those words, some, life, my, whatever, fell out of the top words on both sides. But I think it's just a kind of interesting thing. There's no assurance here. Again, we don't have a formal causal model. This is very speculative kind of, qualitative research here. But, like an indication to us, like something interesting is going on. On the positive reviews, great, amazing, excellent, good, best, wonderful, well. But both genre words are missing. Some is not here, both is not here. I think every single word that we see, so when we first saw these results, it was sort of a sense of like, maybe we didn't just waste, I didn't have any money when we first started in faculty, so it was like a big risk. We're like spending 10K on, or whatever it is, 20K, I don't remember how much, on Mechanical Turk. And we're like, do we just throw out our only cash, to get these, what are we gonna get here? Do we really know what we're doing? And when we saw these results, it was like, maybe something serious is happening. This is kind of interesting. Were any stop words removed? Not from the model, right? Because like a lot of them were there, like my or whatever. It's like the same. It wasn't like we didn't go in and assert. We didn't like go in and like change the stop word criteria between the 3 experiments. It was the same vocabulary. So I mean, the short answer is like, insofar as you saw stop words at the beginning, there was no like pre-processing stop word removal that accounted for what happened between those first 2 models versus when you train on the augmented data. It seems that somehow or another this process of counterfactual, and again, I don't want to overstate the like principle here. Like we do some theory on causal inference. This is much more gestural, but there is some interesting sense in which like somehow this process has sort of like broken some of the associations between, say stop words and the label. So you'll notice if you look here, that, sorry, the chat window is eating just enough of my screen that I don't see my own numbers. Okay. So you could look at it and say, let's just look at the SVM to get some intuition. If you train on the original reviews, and you assess on the original reviews, so this whole first block here is assessed on the original reviews. You train on the original reviews, SVM gets 84% accuracy as assessed on original reviews. You train on the original reviews, your classifier gets only basically the level of random guessing as assessed on the revised reviews. You train the model on the revised reviews, it gets only a little bit better than random guessing on the original reviews, 58% accuracy. But you train on the revised reviews, you get 91% accuracy on the revised reviews. So it's kind of flip. Now, if you train on the original and their revised counterparts, right? So basically all 3.4 thousand data points, then you get 84% accuracy on the original reviews, which is basically as good as you got from the original, just training on the originals. And you also get 87% accuracy on the revised reviews, which is almost as good as you get training just on the revised reviews. So it seems that like there is this model that performs very well on both the original and the revised data that isn't susceptible to these, doesn't need to rely on these correlations in some sense. This model does exist, but if you train on only the original reviews, you get the model that performs badly and on the revised and vice versa. If you train on them together, you get a model that actually performs really well on both. It's not to say you couldn't come up with some other way of altering the data such these models, would still fail. But the point is to say that there's something interesting going on here, that there does exist a model even just within a simple model class. And you see similar patterns for like naive Bayes, 77 down to below 50, 89 down to below 50, train on both, 91 and 86% accuracy, even better than the SVM actually. Random forest, same thing from about 80 down to 58, from 88 down to 57. But if you train on both, you get better, better on both than the model specialized to it. And we can compare just to make sure that this isn't just the fact that you're getting more data, getting 3.4 thousand reviews versus having 1.7. To what if you just got more data? You got 3.4 thousand different original reviews. And you notice it's not so different from the original plus revised, as assessed on original. So it's not that we're just getting, benefit from having data because that model, the original 3.4K, performs really bad on the revised reviews, right? But the original plus revised performs really well on it. So there's something. Sorry, Mohammed asked a question. What does it mean to do well on both original and revised when data is contradictory on the same label? So let me be clear. You say data is contradictory. It's not, I don't know what it means for data to be contradictory. There's no contradiction here. It's that, you have 2 versions of the same underlying review, the original one and the revised version. but the revised version is a different review. It's not that there's a contradiction, it's that they differ in only the ways that actually make the label not apply. Like every other aspect of the review that doesn't actually directly affect the label is unchanged. So you can perform well on the original and revised because it's not the same data point with two different labels. It's two different data points, but one is the revised version of the original. And the important thing is what wasn't revised, right? The important thing is that they revised the genre, they revised the adjectives, they revised, inserted some hedge words, they've changed some opinion words, but they haven't changed who was the actor, what was the genre, did they see it in a theater versus on video? You know, like they haven't edited these things that might have been predictive, but weren't semantically relevant. So in a sense, like these things that weren't semantically relevant are no longer predictive when you have two versions of every review, one where this thing is associated with positive and the other one where this thing is associated with negative. So what we've done in a sense is like we've done informally, we've done something that feels like an intervention to basically create the population, you know, where someone wrote the alternative review versus, you know, we had the population where everyone saw these movies and wrote a positive review, someone had the exact same feelings besides sentiment, but wrote the negative review, and now we're able to sort of, you know, train on them jointly. Here's an interesting thing that we see. We look and say, now this is completely gestural, like what formally relates the distribution of Amazon reviews to the distribution of movie reviews? Obviously, who knows? You don't have an analytic expression for any of these things. There's no graphical model for it. But what we can do is we can say, hey, let's just say, you know, on a lark, let's just apply our models, both the one trained on the original and the revised reviews versus, you know, our apples to apples baseline that gets, you know, keep in mind, the original plus revised has 1.7K reviews, and also those same, you know, bizarro versions, the counterfactually revised versions of those same reviews, which adds up to 3.4K reviews. So the baseline we want to compare against is to make sure that we're not just getting an unfair advantage by, in some sense, having more data to an original, you know, 3.4 thousand original reviews. So we take these two different models, one trained on one trained on the other, and not just two models really, but, you know, the two models for every model class. So from SVM, naive Bayes, Elmo, BioLSTM, BERT. And for each of those, we look at how do these models perform at classifying sentiment on, you know, a bunch of other sentiment data sets, like for example, Amazon reviews, SEMeval, and Yelp reviews. And we find that we never do statistically significantly worse, and we often do much better than the original model. And you could think about why is this happening? And like one kind of intuition would be, well, the model trained only on original data is looking for words like horror that mean negative, or both that mean, you know, positive, or some that mean negative, or romance that mean positive, but those aren't necessarily predictive. And they might even have opposite correlation, some of those words, on say Amazon reviews. Like what binds them to the label isn't like actually, you know, that this is what, you know, these words mean, and that, you know, they necessarily connote, you know, positive sentiment. So we see even an interesting thing that we find is like in general, you know, and there's something interesting to be explored here about why pre-training is so effective, but, you know, for some reason, something to do with the fact that they're maybe exposed to such a wide diversity of text, where, you know, BERT models in general exhibit the same qualitative pattern over here, but the drops are less precipitous, you know, from 87 to 82, from 91 to 77. Those are big drops, but they're not like from 84 to random guessing, something like that. But they still have the same qualitative pattern. And same over here, we find that, you know, across all these experiments, the model trained on the original plus the revised reviews is doing better on all of these different out-of-domain data sets. Again, there's no such thing as saying, oh, I have a model that in general is good out of domain. That is an underspecified kind of claim. But this is, you know, hopefully at least, you know, suggestive, something interesting is going on. So I'll just kind of wrap up a little bit because, you know, I think we started late, so maybe I'll get like 5 minutes. Is that okay, Seth?
Yeah, sure. Keep going, and then we'll take Q&A. Since I'm breaking in, attendees can use the Q&A feature to enter questions, or if you raise your hand after Zach is done the talk, I will voice enable you to ask your question interactively.
Yeah. Okay. Some questions. Kat asked, do you think causal inference without humans in the loop is possible? Could ML incorporate the do calculus? So in general, statistics and like causal and statistical procedures are sort of like not either or. They like data, like there are certain questions that data alone cannot answer. And that's like the fundamental problem of causal inference that is like well known. Like if you take like causality 101 with anybody who knows what they're doing, you know, there are some questions that basically like, if I just give you like data points X and Y that are jointly Gaussian, you can't tell me does X cause Y or does Y cause X, and no amount of data will tell you that. So like pure just like model free ML cannot answer that question. And I think an ML incorporate the do calculus. What the do calculus does is the do calculus is a procedure for basically saying, okay, if I know the underlying model, if I have a graphical structure that tells me the way that my variables are related to each other, you know, it's basically a generative process for creating the data, and says the important things are which variables listen to which other variables and which ones do not, and such a that this forms like a directed acyclic graph. The do calculus tells me if you give me a causal quantity of interest, like what is the difference between the expected, you know, lifespan if I give the treatment to everyone versus if I give the treatment to no one. What the do calculus says is, given the causal structure and given this causal question, I can basically run the do calculus, and there's like, you know, what do they call it, the something ID formula that like Yuta Pearl and Spitzer came up with. It's like an algorithm. It's computationally difficult, but what basically the do calculus can do, the do calculus is basically a set of rules for manipulating causal functionals into equivalent functionals. And basically, what word were we saying before calculus? Do calculus. Like what is the, like it's for basically the goal is you want to get from a statement like what is the probability of Y given do X, where do X means you set the variable X to some value regardless of what value it would have naturally taken. So the classic example would be a treatment. Like, you know, I don't just want to look and say, what's the probability that you die given that you were given this drug, given that you took some drug, because you might have been assigned that drug because you were, you know, a higher risk patient in the first place. So you might be more likely to die if I just look at the probability that you die given that you received a particular drug, even if the drug is beneficial, right? And so what I want to know isn't what's the probability that you die given that you received the drug, but rather what is the difference between the probability that you die given, you know, if you receive this drug, or, you know, the probability that you die if I were to intervene and give you a different drug than what you otherwise would have been assigned, right? That's what causality gets at. So in short, you know, like a pure just like here's the data, dump it in the black box thing, that the do calculus requires more than that in the first place. The do calculus requires a structural causal model, and that then the do calculus is applied to that model together with your set of, you know, this is the model, this is the causal quantity that I want to estimate, and this is the subset of variables that I actually observe in the data. And the do calculus could be applied to basically eventually tell you either, yes, this is something you could be estimated, that can be estimated from the data you have, or two, this is something that's not even possible to estimate from the data that you have. And then if it is estimable, to say, here is basically a traditional statistical quantity, we call an estimand, right? So like probability of Y given X is a statistical estimand. Probability of Y given do X is a causal estimand. And in order to translate a causal estimand into a statistical estimand, what we need is assumptions. What we need is a causal graphical model. And so the answer is, can you do it without humans in the loop? In a sense, no, in that you can do it without structural knowledge. And so typically in traditional causal inference, the way the structural knowledge comes is because you say, I have domain expertise, or I've done, I know something about science, or I've done experiments, and therefore I know the structure of the graph. I don't know, you know, I know that the treatment can either cause, that the treatment can cause, you know, the side effect, but the side effect doesn't cause the treatment. Like, it doesn't mean that I know whether the treatment makes the side effect better or worse. It doesn't say anything about the direction or magnitude of the cause, but it says that I know what variables respond to what other variables. And so like, I know, the way this is stated in causality is like, I know which way the arrow points, right? And so you always need humans or domain expertise or something to give you that knowledge. the question that we're getting at here is, what do you do in a world where the data is so complicated that we can't draw a simple causal model, not at least a literal one. We can't do just traditional, we can't do calculus on documents. So what we have to do is like have a slightly higher level of abstraction, and then think about what are clever ways that we utilize the resources around us to get to something that maybe qualitatively is like a causal manipulation. What is a sampling procedure from an original data set? I'm trying to say what is going on. Take a look at some of these questions.
We have a question from Risha Gupta, who I voice enabled. Risha, do you want to pose your question?
Yeah.
Sure. Hi, Zach, this is very interesting. So you were, okay, so I have two questions basically. One is for text data, it kind of seems intuitive. You've also spoken about how like we can do this for other kinds of features, but how do we even start to think about it when it is like numerical features, numbers, and we don't exactly understand what we are looking for? And the second thing, when do you stop? So for example, in the slide you showed that for the word dawn also, you know, you were kind of doubting if it is connected with like a bad review or not. But what if we start tweaking for reviews that contain the word dawn, and then like how do you know you are done?
Yeah, so there's a couple of things. One is that in a sense, numerical, like I don't think this is like appropriate for cases where people don't know what's going on. The whole point here is that like we're exploiting a case where we don't know how to write a graphical model. We have no idea how to formalize it in this kind of reductive way. But at the same time, we're exploiting the fact that actually humans are the generative model for text. Humans do know when a review is positive and when it's negative, right? And they have high like agreement among each other even on that point. For numerical features, well, if you're talking about tabular data, you know, in some sense, you're in a problem that was better suited in the first place to the traditional tools of causal inference, right? But like, you know, I think the case where your data is tabular and where you know, don't know how to manipulate it to, you know, produce the counterfactual, that would be a situation where this technique is not applicable, but actually where, you know, the traditional tools are more applicable. When you talk about like the word dawn, I mean, I want to be clear that like, I don't think that like looking at the coefficients on the TF IDF words, you know, is a super principled thing to do. I was just giving some intuition. In general, we're not going out there saying like, show us what we want to see. We didn't say to them, edit, but don't change the word horror because we saw the word horror in the top features, and you know, we know that shouldn't be there, so we want to get rid of it. We're not pre-specifying that to anyone. The important thing here is that we're just going to people and saying, please edit the review so that it agrees with the counterfactual label, and don't change anything unnecessarily. So people are revealing to us, you know, which things seem to be things that need to be edited versus not. And that knowledge is what's enabling us to get out these models that have these interesting properties. But we're not telling them what to do. So I think you want to be very careful about, this is why I think the entire interpretability literature has just gone completely off the rails, is you have a whole culture where it's sort of acceptable to not even ponder in the first place what scientific question you're asking, and just to kind of like be driven entirely by a sort of confirmation bias of, you know, we want the model to look like this, so we do this, and then we change the, you know, oh, the saliency map looked like that, but then it highlighted this thing we didn't want it to do, so then we added this, and then we ran the experiment again, and then it looked like what we wanted to see. That's not, you know what I mean? It's like, what were they doing in the first place? They don't know. They were just, you know, there's this way that like an entire literature is sort of off the rails and just acting sort of reactively, but not asking any clearly articulated scientific questions. For us, we don't want to tell people this is what we want to see or not want to see. We are asking people to edit the reviews in a particular kind of way, and then we are kind of analyzing this, yes, qualitatively, but also quantitatively. So how do you handle mixed reviews? You know, this is sort of up to people's idea of what's acceptable. Like, I don't think I loved the beginning but hated the end necessarily like conflicting with some, but you know, people have to make judgment calls about what do they think makes the review inconsistent versus not. with a label. Like you could say, I loved the beginning of the movie, but hated the ending, but then have it overall be a positive review. Maybe. I mean, it might depend upon the rest. But again, I want to be clear, Seth, that like we're not telling people like this is part of the whole point here, is that we're not going to them telling them how to handle it. We're saying, here's the review, edit it so that it agrees with the other label. Don't make unnecessary or irrelevant edits. But beyond that, we're sort of learning something about, we're exploiting how that, you know, people have their own, you know, kind of commitments and ideas about what, you know, makes, what needs to be edited, or what needs to be edited most, and at what point the review is, you know, sufficiently clearly positive, and you know, what constitutes a contradiction and what doesn't constitute a contradiction. Cool. All right, I'm gonna just like finish up just a little bit. Let's see, we're at 2:15. I just want to like kind of give a little gesture here about, you know, just maybe spelling out some of the things that we already kind of talked about them informally. But, you know, one thing that we kind of did afterwards, and this is a follow-up work that is at ICLR this past year called Explaining the Efficacy of Counterfactually Augmented Data, is to sort of say, okay, this idea sort of seems intuitive and kind of makes sense. We're getting these interesting results, but, you know, we want to be a little bit clear about, you know, in what sense, you know, what do we really think is going on here? Even if we can't really draw a DAG that, you know, is in terms of the, you know, word, you know, at the level of like words in a document, can we write a DAG at a higher level that kind of at least convey some intuition about what we think is going on, or what is the right abstraction for even thinking about counterfactually augmented data? Can we come up with some arguments that are a little bit more formal to help us, you know, articulate why do we think this ought to have out of domain benefits? And, you know, can we verify that actually what we're getting out of these annotators is something that is qualitatively beyond what we're able to achieve, you know, just, you know, using, you know, kind of standard associative tools that are out there. For example, you can imagine doing style transfer type things to make positive reviews negative and negative reviews positive. And like, if we use such a model, do we get the same kinds of improvements? Did we really need humans all along? Could we just have used an off-the-shelf model, or are we really, you know, getting at something here that wasn't just obvious only from associations? And so, you know, we look at these things at a high level, like, you know, we make some kind of simple, you know, maybe slightly banal observations, but that I think are useful for forming intuitions about just simple linear Gaussian models. So for example, if you have a graphical model where you have two features, so we call this the causal setting. The causal setting meaning that when we imagine that the way we're thinking about this is that the features cause the label to apply or not to apply, we might imagine that there are sort of two groups of features, the features that are actually causally relevant and the ones that are not. And if these features are uncorrelated with each other, you know, the model, you know, X1 and X2 here, X1 causes the label, X2 does not. If these guys were uncorrelated, like if there was no confounder Z, then, you know, no model that you would train, you know, but for like some finite sample issues, no model that you would train to predict Y given X1 and X2 would actually rely on X2, right? On the other hand, if X1 and X2 are highly correlated, then things change, right? X1, a model trained to predict Y given X1 and X2, if it's a linear model with no regularization, and this is a linear Gaussian model, will again also only rely on X1, like the value, you know, there might be a spurious in the sense of a finite sample effect, but in expectation, the coefficient of, you know, regressing Y on X1 and X2, the coefficient, the partial, you know, regression coefficient of Y on X2 is going to be in expectation 0. However, if you use regularization, the model would now actually, in expectation, assign weight to both X1 and X2, right? Or if you didn't actually observe X1 and X2 directly, but X1 and X2 were both noisily observed, then also the model would give non-zero weight to X2. So there's this interesting kind of dynamic that, like, well, whether or not you directly observe the features, or the features are noisily observed, or whether or not you have regularization, all influence whether or not your model is going to rely on the sort of spurious correlate. We can flip things around and say, what if we imagine that like Y is the label, and this causes, you know, some subset of your features, but Y is associated with other factors. Like Y could be the sentiment that the person feels, but Q could be like some non-sentiment aspects of, you know, their impressions of a movie, and these both result in, you know, different aspects of the review. However, if you have this model, but they both have a confounder because they're both based on having observed the same film, and so these different sentiments, like these different latent factors of the review, can all be correlated with each other. And in this case, we think what's going to happen if we train y, if we regress y on x1 and x2, and indeed, y will depend on both x1 and on x2, whether or not there's noisy measurements. And in both cases, we can see what's going to happen. What do we think is happening in counterfactually augmented data? Like one way we could formalize counterfactually augmented data here is you could say, well, we're asking someone to keep all the underlying factors, latent aspects of the review constant, but to intervene on the label and sort of re-render x1. And if we do that, and then you train a model to regress, y on x1 and x2, the model will not rely on x2. And why? It's like, well, once you intervene on y, you basically drop the incoming arrow. You've deseparated y from x2. So, we can come up with some kind of high level models that then lead to, some hypotheses about what should work, what should be useful under certain types of out of domain perturbation and why. So we do a bunch of these different experiments and find that like on real world data sets, they tend to be confirmed by things that, either are what sort of we conclude to be the causal spans, or what are marked from like feature feedback data sets that others have collected, and how that contrasts with what you get from doing like style transfer, or looking at like, the spans highlighted by attention maps or some other kind of heuristic like that. So, we also have some experiments showing that like, you could compare the results from using counterfactually augmented data to the performance that you would have gotten if instead you used some style transfer method to try to render the counterfactuals versus humans, and then evaluate either in or out of sample. And we again see basically you don't get comparable results. So in fact, most of those models do worse than if you just use a model trained on the original data, whereas we get big advantages from using counterfactual augmented data. So in general, at a high level, this is an area we're excited about. I don't want to overstate the rigor here, that it's very much kind of like, was it blue skies, blue oceans or something, as we're very much, I think, striking out on a path that it's in dialogue with some, I think, mature methodology, but at the same time, applying some of it in a very gestural way, and getting at some, interesting, but still very exploratory experiments. So that's my story. Thanks for hanging out. Thanks, Seth, for the invitation. If you're interested in following up, I'm on Twitter, and I have a lab website. You can follow the great work that my students are doing while I get old, and just try to stay somewhat useful to them. The papers I focused on today really are principally these two: learning the difference that makes a difference with counterfactually augmented data from ICLR 2020, and the follow-up from ICLR 2021. I'd like to thank some of my sponsors, and these include faculty awards from AWS and Salesforce and Facebook, and my medical collaborators at UPMC and Abridge and at Highmark, and the NVIDIA AI Lab, the Center for Machine Learning and Health, the Block Center, the NSF, and SEI and DARPA. So I will stop my share now, or maybe I already did.
Yeah, you already did. All right, well, thanks very much, Zack, for speaking today. Yeah, as you mentioned at the beginning, it took a while to arrange this talk, so I'm glad we could finally do it. And I will share my screen again. So to remind everyone that, let's see, that should work. Remind everyone that I will post video of this session along with all of the previous sessions on the NLPXING, which is that character you see there, YouTube channel. And then further, if people in the audience now would like to propose a talk, it can be anything from 10 minutes up to a full length talk like the one we had today for a future session, then you should send me a note and we can discuss that. And then finally, we have the next session on the schedule for June the 15th, Amazon Data Tuner. So I hope you all can join that. So we'll wrap up for today. thanks everyone for attending. I do see that Zack has put his GitHub in the chat there. I will post that to the comment section along with the URL for the video for today to the meetups where this program is listed. So thanks everyone for joining us, and we'll see you next time.